All right. Take all these off, I guess. Okay. So this lesson is the final lesson in our first unit. Or I guess it'd be more accurate to say it's the second last lesson, because the last lesson about intermolecular forces I've asked you guys to do independently. But today's lesson is a brief one, and it's an important one, though not one we're going to spend a lot of time on. Though you'll spend a lot of time talking about it in university. And the reason I really want to focus on is you're also going to spend a lot of time talking about these concepts if you take biology throughout. These concepts are really, really important in the biological sciences. So today we're talking about polar bonds and polar molecules. And you should remember, of course, that a polar bond is a bond between a covalent bond between two atoms in which the electrons are not shared equally. And so today we're going to talk about how polar bonds give us polar molecules. And the first thing we want to point out is that if the bond isn't polar, the molecule can't be. So I want to draw the example of carbon disulphide. And if we were to, draw a Lewis diagram for this, we would put carbon in the center and sulfur around, because carbon has a lower electronegativity than sulfur. We would put a sigma bond between them. We would fill the surrounding octets. And we would count electrons, knowing that carbon should give us 4, and sulfur should give us 6 each, for a total of 12, for a total of 16. And if we look here, we'd go 2, 4, 6, 8, 10, 12, 14, 16. So we would see that we have to apply double bonds. All right. And quickly, we would know that we have 2 pi bonds here. So that carbon must be exhibiting sp hybridization. And it must have a bond angle of 180 degrees, all that from yesterday. None of that really applies to today's lesson just yet, though we're going to talk about it. But I don't need to change the shape of this. It's drawn right. It should be a straight line, just like that. It is linear, because anything with sp hybridization is linear. So now, to ask myself, is this molecule polar, which is what this lesson is all about? Does this molecule have partial charge? Is it polar or is it nonpolar? Another way of asking it would be, from your intermolecular forces assignment, is this going to show dipole-dipole interactions, or will it only have London dispersion forces? And the quick way to tell is, the first thing we need to look at is the bond polar? So here we have a bond between sulfur and carbon, and we have to look at the difference in electronegativity. Carbon has an electronegativity of 2.55, and sulfur has an electronegativity of 2.58. I'll put the little periodic table in here for you. So those numbers are. And if you look, I've already done the math, the difference in electronegativity here is only 0.03. And if you remember, we typically define as polar anything from 0.3 up to 1.7. You'll see some textbooks that say 0.5 to 1.7. You'll see others that say 0.5 to 1.5, but we'll work with this as a definition. So by any stretch of the imagination, this difference in electronegativity is really low. At just 0.03, we say that the difference in electronegativity isn't in this range, so it's not a polar bond. So the bond between sulfur and carbon isn't polar, and so the molecule on the whole can't be polar. And I hope that makes sense. So when we draw a diagram, we don't have to ask anything else. If we look at the difference in electronegativity and it's very, very low like this, we can say this is not polar, because the difference in electronegativity is too low. And I want to contrast that with a different compound. If we look here, we're going to look at hydrogen chloride, HCl. You may be tempted to say this is hydrochloric acid, but we're actually going to talk about it in its gaseous state here, how a different way that it can exist. So hydrogen chloride, and if we were going to draw a Lewis diagram for this, we would say that hydrogen is going to give us 1 electron, chlorine is going to give us 7 electrons for a total of 8. We would put them together with a sigma bond. We would look at the hydrogen. It already has a, oh, what am I doing? There we go. We would look at the surrounding atom, which we typically think of as the hydrogen here. We'd say it already has a complete octet. But because I only have 2 electrons and I need 8, we fill in the difference on chlorine. And now we have a stable molecule. So this is the Lewis diagram of hydrogen chloride. And here, if we look, the difference in electronegativity is equal to chlorine's 3.16 minus 2.2 for hydrogen. And if you do that math, you should see that the difference in electronegativity ends up being 0.94. Excuse me. Oh, sorry. 0.96. So that electronegativity is big enough for the bond to be polar. And note, it's low enough that's not ionic. So there's not a transfer of electrons. It is polar. But this tells us that the bond is polar. And we show that over here by actually drawing a little arrow over top of this. And it's an arrow with a tail there and a tip here. And this arrow tells us that we have a dipole here. And the tip of the arrow is where the negative charge is. So we say this is where the slight negative charge is. And that symbol that looks kind of like a not quite finished 8 is a lowercase Greek delta. It just means partial. And the slight positive is on this end of the dipole. You don't need to draw these in the future. I'm just showing them here to show that's where the poles are. So quite simply, the electrons spend more time with chlorine. This side where the tip of the arrow is negative, and the other side where the tail of the arrow is, that's positive. And that arrow is how we show it. So up until now, we've always said that this is it. Either the difference in electronegativity is low, in which case it's not polar, or it's big enough that it is polar. What I want to show you today is that these dipoles can cancel each other out. And the first thing I want to look at is boron trichloride. So in this case, we have boron and 3 chlorines. Well, 3 chlorines gives us 21 electrons. In its valence. Excuse me. And then boron gives us 3 in its valence. Right? If you look here, it's in group 5. So it's got 3 electrons in its valence. And that gives us a total of 24 electrons. So when we go to draw this, we put a boron in the center because if we look, it has the lower electronegativity of the true. And around it, we put chlorine, just like that. Chlorine, chlorine, and chlorine. And we fill in the surrounding valences. And then we just count electrons. And we should have 24. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which is enough. So I don't need to add any electrons. But we know that boron needs 2 more to have a complete octet. So we're going to share a pair of electrons with the chlorine up here. And again, if we look really quickly, we'll say that this is sp2 hybridization because we have 1 pi bond. And we said yesterday that everything that has sp2 hybridization is 2-dimensional. In this case, we say it's that flat triangle. It's trigonal, planar, all right, and the bond angle is 120 degrees. And really quickly, we want to look and see that these bonds are polar, all right? The difference in electronegativity is 3.16 minus 2.04, and that, excuse me, works out to 1.12. And that is enough to give us a polar bond, which means that here, the electrons are always going to spend more time with chlorine. So in this bond, the electrons spend more time with chlorine. In this bond, the electrons spend more time with chlorine. And in this bond, the electrons spend more time with chlorine. And we're going to ignore the double bond, the pi bond, and I'll tell you about why at a future date. You don't need to worry about it. But what I want you to see is that these arrows actually work to cancel each other out. If we look at them, one tells us to go up here, the other to go down here, and the other to go down here in this direction. And you can imagine that if you were to follow these steps, if you walked forward, 5 steps, then turned 120 degrees to your left and walked 5 steps, and then turned 120 degrees to your left again and walked 5 steps, you would actually end up right back where you started. These 3 lines cancel each other out. So we say that even though it has 3 polar bonds, this whole thing is not polar, because the dipoles cancel each other out. All right, and that happens because they're symmetrical. All right, and so if we were to redraw this whole thing, but if we replaced one of those chlorines with something much closer to boron's electronegativity, say a hydrogen, we would end up with a different situation. So if I had boron bound now to hydrogen, chlorine, and chlorine, in this case, we would say that there's a dipole here and a dipole here, but no dipole here. And in this case, we would end up with these 2 adding together to give us an overall movement in this direction. And so we would say that this is polar, all right? Because the dipoles don't cancel. And the long and the short of that is, if all 3 of the bonds in this case are to the same thing, then they're going to cancel out. But if 2 of them are to the same thing and the third one is to something different, they don't cancel out. And this also, by the way, could just as easily have been a lone pair of electrons. And if it were a lone pair of electrons, these 2 dipoles would still not cancel out. So anything other than another chlorine will let these dipoles make the thing polar, as long as it's not symmetrical. And that's the rule. If the molecule is symmetrical, it cannot be polar. The last thing we want to point out is that this dipole can cancel itself even if we're looking at things in 3 dimensions. And the example I give here is CCl4. So here again, we would say carbon gives us 4 electrons, chlorine gives us 7 each. All right, but there's 4 of them, which is going to give us a total of 28. And just to do it quickly for you, what we end up with is a structure that looks like this, all single bonds and lone pairs, because that works out to 32 electrons, which is what we're supposed to get. And so you should really quickly look at that and see that it's sp3 hybridized, all right, because there's no pi bonds. And so that should really quickly tell you that this is a tetrahedron. All right, 109.5 degree bond angle. All right, and then if we looked at the difference in electronegativity, we'll see that chlorine has 3.16 and carbon's is 2.55. And that works out to a difference in electronegativity, excuse me, of 0.61. All right, and that means that it has polar bonds, which means that we have to come in here and draw dipoles. So we have one dipole here because the electrons are going to spend more time with chlorine than they do with carbon. We have another dipole here because, again, more time with chlorine. We have another dipole here down towards this chlorine. And we have a final dipole here down towards this chlorine. And it's a little awkward to draw these, but if you put them together, you'll see that, again, they're perfectly symmetrical. So we have one dipole going straight up, one dipole with it like that, one of them coming forward towards us, like this, and one of them heading away from us, like that, badly drawn, and they cancel out. Again, you don't have to draw it like this, but what we know is it cancels out because they're symmetrical. Because we know hybrid orbitals always try to make the angle between them perfectly equal. And so the dipoles end up all going in exactly opposite directions. And so this would be not polar, again, even though each of the bonds is polar. And the last thing to show is that if we change just one chlorine out for something different, so if I replaced a chlorine, say, with a double bond, so say I had Cl here, here, and here, and instead, or a lone pair of electrons, or even a hydrogen. And actually, let's do that. Let's say we have carbon to chlorine and chlorine. And this one's also chlorine. But now this bond heading backwards here isn't to another chlorine, but it's to a hydrogen. Well, now we would have a dipole going this way, a dipole going this way, and a dipole going down towards the chlorine, but we wouldn't have a dipole going back towards the hydrogen because that bond isn't polar. And so we would end up with these three that would produce a net dipole. And so we would say the molecule is polar because it's not symmetrical. All right, and there's a great video I'm going to post next to this of a British chemistry teacher. He's a lot better than I am. Explains it a lot more clearly. I'm going to use some really good animations that I think show it well. So this lesson here kind of shows you the note we did, but he's going to show you well, and it ends with this really great animation showing the concept, which I can't stress enough. So I encourage you to watch that. It's attached on this site. And when you finish with this, you've got time to work on the rest of your assignments that are due. Thanks for watching.